So yeah, if you were here last week, or yeah, last week I talked about two very important events in the early 20th century that motivated modern physics. And so, in particular, the one I want to bring your attention to from last week was the UV catastrophe. Basically, our model for blackbody radiation initially was dependent on treating light as a wave, and that allowed infinite frequencies basically from a black body, and that meant that you had some frequency you could have infinite frequency, which meant your temperature of your black body would also go to infinity, which is not good. That's not We don't see that in reality. And so the solution, um, so what Max Planck did to fix this was instead of treating light as a wave, he said that the light emitted could only be emitted in discrete packets of energy directly proportional to the frequency. And if you substitute this in and redo the derivation for blackbody radiation, you get a finite kind of skewed bell curve looking thing. And so that basically it made the blackbody radiation finite, which is good. And so this notion of discrete packets of energy, he called quanta, which means like discrete. Um, but the important thing that I want to bring up is not just this notion of quanta, but the fact that the UV catastrophe and what Planck did was not an experiment. In contrast to the other thing I talked about last week, which was the Michelson-Morley experiment, Planck did not run any experiment to prove this. He was a pure theorist. He just fixed the math to get it to work or to get it to match with reality. So, this week, I want to talk about two experiments that solidified the idea that light truly does behave like a particle in some situations. Those two experiments and subsequent effects being the photoelectric and the Compton effect. So, with that in mind, let's start with the photoelectric effect. Yes, exactly, Carmomo. So the photoelectric effect, an important thing to know about this was actually observed prior to 1900. Scientists had already observed this phenomenon in the lab prior to the 1900s. There were scientists that observed that when you shot a spark gap with radio waves, it would cause sparks to occur. Um, and the issue was just it, the issue was that they didn't have an explanation for it. So they knew this existed, they just didn't know what caused it. Because um, acted as a wave, then the um, then the energy of these electrons that the photoelectric effect emits or kicks off should be proportional to the intensity of the light. This is not what they observed. Instead, they'd observe that the energy of the kicked off electrons was directly proportional to the frequency of the light, not the intensity. Um, and so, um, the solution came from Einstein. Um, so Einstein proposed that this photoelectric effect is caused by incident photons, these discrete packets of energy. I'm going to use gamma to represent a photon. It is incident on some metal, and this light, this packet of light, collides with some bound electron in this metal and ejects it. And this can only occur if light behaves as a particle, because this is essentially a collision that's occurring. Hey Aggie, how are you? Um, and so yeah, in this model, um, okay, so yeah, so in this model, this corrects the notion that this photoelectric effect is dependent on the frequency of light rather than the intensity. And so again, Einstein was also just a theorist. He didn't do any experiment, even though he was credited, like, because his solution actually explained the photoelectric effect. He was in fact given the Nobel Prize for it in 1905. Um, but he did not actually do the experiment that proved his solution correct. Yes, he was an uber nerd, as one might say. And so the experiment, which was done by many people, um, Millikan was one of them. So the experiment diagram kind of looks like this. So you have a cathode and an anode, right? Or two electrodes. You have two metal plates, um, and you enclose it in a vacuum, so that the electrons don't collide with any air particles and make it lose energy. And you connect it to a battery and a voltmeter. Or sorry, not a voltmeter, an ammeter. You want to measure the current. So, what ends up happening is, let's suppose you shine light so that it hits this electrode. If so, because of the photoelectric effect, light will hit this electrode, it will knock electrons free, and these electrons will travel to uh, this electrode right here. And because you have now completed the circuit, because before no electrons were flowing across this, because you have completed the circuit now, you have a current in this direction. Or I think technically it's measured reverse, but either way, you have a current generated because of this now. You've completed the circuit. So that means you should have some non-zero measurement in your ammeter. Um, excuse me. So that's without this battery. If we put this battery in, and in fact we kind of want a variable power source, that's what that arrow means. Um, we want to apply a backwards voltage across this tube. We want to slow down. We want to impede the flow of these electrons, and the reason why is because I haven't gotten this far in my E&M lectures, but the potential energy caused by an electric potential difference is equal to the electric charge. In this case, it's called little e. It's the charge of an electron times the voltage. So, um, thinking about conservation of thank you. Thinking about conservation of energy for a bit. So, that vacuum tube, right? The electrons should only be affected by that voltage. So that means if we apply enough voltage, let's call it V stop. If we apply enough voltage, it should actually completely stop the electrons before it hits the other electrode. So all that kinetic energy the light just gave it should be stopped. So we can set that directly equal to the kinetic energy of the electron, and I'll say max because there's some variance involved. Um, and so what they ended up doing was they slowly increase. This is weird. Hang on. No, hang on. I do not know why I'm writing slanted right now. Hang on. Okay. So, the purpose of this experiment, you shine a monochromatic light source. So, you want all this light to be of the same frequency. So, when this experiment was originally done, they didn't have lasers. So, what I think they did was they used like a light bulb and just put color filters in front of it, or use some other source that they knew had a single frequency. Um, but yeah, so what you do is you increase V, or not V stop. You increase the voltage. So, like I said before, without that battery, if you shine the light, you create a current, and you can measure that current with the ammeter. When you increase this voltage enough such that you hit V stop and you stop all of these electrons, you now break the circuit. Since electrons can no longer make it to the other electrode, you don't have a complete circuit, which means at that point, your measured current in this ammeter should go to 0. So you increase V until your measured current goes to 0. And that is your IV curve, essentially. Ah, so this will tell you effectively. So if you plot this versus voltage, you'll end up seeing, so if this is 0 voltage, you'll have some constant value because um, forward voltage doesn't affect the current as much. But as you apply the reverse voltage, it'll slowly go down until you hit 0 current, and this is your V stop. The other part of this experiment, which is what gives us the equation for the photoelectric effect, is when you change the frequency of the light incident upon it. If you do that, and you still measure the current based off of this procedure, so if you change the frequency and you do this IV curve again to find V stop, that tells you the kinetic energy of the electrons, then you can plot um, F versus the kinetic energy, and what you get looks like this, which is a line essentially. And so that tells you that the kinetic energy, if you fit this to the equation for a line y equals mx plus b, you get, I'm going to leave it as m for right now, mf plus B. So MF, this should be the energy of a photon, right? So this ends up actually being Planck's constant. Um, and this B, this y-intercept, right? If you'll see, this would correspond to this line getting shifted down. So I'm going to say this is equal to some minus phi. This corresponds to physically, there is some minimum amount of energy that the light needs to have to actually kick the electron out. If your photon isn't energetic enough, it won't kick it out. And so this is called the work function. And this corresponds to, actually, let me write this out first. So all in all, we have that the kinetic energy is equal to hf minus phi. And that is the photoelectric effect equation that got Einstein his Nobel Prize. Before I explain what this work function specifically comes from, do you have any questions? Sort of. So, yes, in order to kick any electrons out, you need the photon to have at least the same energy as the work function. So that means that your F minimum, you can actually calculate your F minimum for whatever material you're looking at by setting this equal to 0. So then you have HF equals phi. So that tells you that the minimum cutoff frequency is phi over H. And so at the time, all they knew about this work function was that it's dependent on the electrode material. But that's all they knew about it at the time. All they knew was that it just depended on what material you were hitting the light with, or light at. So, in modern times, after having a better understanding of atomic and molecular physics, we now know that this work function ends up representing, if you have some material, you have these energy levels. And in metals, you have this kind of band called the conduction band. And so this is E on the y-axis. And so at some point, you get zero energy. This zero energy is what's called continuum. Zero energy is when we consider the electrons bound by the material to be free. They're no longer subject to the attraction caused by the nuclei. So the work function ends up equaling the energy required to free the electrons from their bound states. But again, they didn't know that at the time. They didn't have material physics. They didn't have solid state. They just knew it depended on the material. Not only was this an important experiment and discovery in showing that light had both wave and particle properties, this effect actually is very important nowadays for things like photovoltaics and photomultiplier tubes. So if you want to detect like a really weak light signal, you'll use something called a photomultiplier tube. It's a series of these electrodes, right? So the small amount of light comes in, it kicks off some electrons because of the photoelectric effect. It'll hit the second electrode, and those electrons, because of their energies, will kick off more electrons, and it creates some cascade until eventually you get enough electrons that you have a measurable current.